Aaron, if you would like to
Okay.
begin.
All right, so I was asked to talk about Cauchy slice holography, and while I will keep talking, as long as none of you are talking, this is meant to be a bit of a discussion where you can ask questions and guide the direction that things go. So the main idea is maybe based on an analogy that once I saw I could unsee it between the wave function and of the universe and partition functions. So the fundamental equation we're going to be looking for is something like a theory's partition function of a metric and maybe some other fields, and we'll just start with the metric for the time being, is going to be a Wheeler-DeWitt wave function of the same metric. So over here, you're regarding the metric as a source, and over here, you're regarding it as a configuration space variable. So there's an extra dimension here. So this is a d-dimensional field theory. And this is a d+1 quantum gravity. So this is a holographic dictionary. And it's going to turn out that the thing that does this for you is the TTbar deformation. But the thing that's going to make it Cauchy slice holography is we'll be interested in this theory as it exists on a space-like surface where time is the emergent dimension, and so this +1 is the time direction as you would usually have in the Wheeler-DeWitt formalism. So if you think about what you do with partition functions, what you like to do with partition functions is define a stress tensor by differentiating.
More precisely, it's a partition function of a quantum field theory.
It's a partition function of a QFT, only it's not unitary, that is obtained by starting with a normal holographic CFT and doing an irrelevant deformation to it. So it's a partition function of this thing called T squared. It's called T squared because the deformation includes a term that's quadratic in the stress energy.
And it's a partition function of closed, compact, d-dimensional.
It doesn't have to be closed. You could consider both
Partition
cases.
function of d-dimensional manifold.
Yes, you can pick your metric and then evaluate this.
Okay, and if it's not closed, then it's also a function of boundary conditions.
That's correct. And the fact that it's a function of boundary conditions actually allows you to junction this with the usual holographic ADS CFT. So if, for example, I have some space-time, like I don't know, an internal black hole or something, and I have some Cauchy slice of this thing that stops at the CFT boundaries, that the necessary boundary condition for this theory is going to be the same as the usual states of the CFT. And that means that this TTbar partition function is actually going to be usable to give maps between boundary states and Wheeler-DeWitt interiors. So one perspective on this dictionary is it's like a geometrodynamics version of the ADS CFT dictionary, where if somebody hands you a CFT state, you can directly work out, assuming you have knowledge of this partition function, what the corresponding Wheeler-DeWitt state is in the bulk.
Okay, so the CFT state is in spatial slice and D-1 dimensions.
Yeah, so the states would live in D-1 dimensions, yeah, so. Or, so if I cut this thing somewhere that wasn't at infinity, I would be discussing states of the deformed field theory, and that's also a very interesting story. But when I go out to infinity, the irrelevant term becomes, well, irrelevant. And so it's the same as the usual CFT states.
Okay, and the theory on sigma, what is the quantum theory on sigma?
It's a quantum theory on sigma, where you regard its metric as a fixed
Yeah.
source.
Just a couple go back.
That's right. Right. So even though the source is fixed, you can differentiate with respect to it. And that is what gets you the stress tensor of the theory. Okay, on the Wheeler-DeWitt side, we would write down a similar equation in terms of the ADM momentum. So that's like minus I, the derivative with respect to the metric, okay?
So may I understand this as usually ADS safety, the safety is in the flat space, but now you basically change it to any background metric in the on the boundary field theory.
Well, even in the case of the holographic CFT, you could have picked it on a different metric.
Yeah, okay.
Though it's conceivable that if the metric is too different from the usual cases, the theory could be unstable and ill-defined or something. Actually, this is something that worries me a little bit about this story, because if you put something like, for example, n equals 4 super Yang mills on a compact, negatively curved space-time, then because the scalar fields are conformally coupled, it looks like a tachyon field. And then it looks like the partition function is unstable. So maybe since the irrelevant deformation is sort of like something morally like diffusion over the space of metrics, you could worry that this sort of problem with the initial seed CFT is going to contaminate the definition of this theory at some level. So that's a problem I have not fully come to terms with here. Or a potential problem. I don't know if it's a problem, but it might be a problem.
I mean, would the Wheeler-DeWitt wave function be expected to have pathologies on such measures?
No, I don't think so.
And one more thing is for the Wheeler-DeWitt wave function, which is the one dimension higher, the G should correspond to the G on the Cauchy size is sigma, not
G
just.
being the metric, that's right, right, so this is a spatial metric. So some people would call this Q or something.
Oh, yeah, but now, but on the left hand side, the G is the boundary G. So this means you assume there is a unique extension from boundary G to a box G.
No, this G is the metric of this Cauchy slice sigma.
Yeah, but on left hand side, just have a D-dimensional. So in the left.
That's right, so the Cauchy slice sigma is D-dimensional, the bulk is D plus 1 dimension.
Oh, that's another bound. Oh, that's not bound. Oh, that's.
Right, this is D minus 1.
Oh, okay.
As is this, sigma is D-dimensional. And this whole space-time is D plus 1 dimension.
And what's the point of the t-squared deformation? Why wouldn't you just postulate this for?
Right, so this can't be a normal field theory, because what we know is that the Wheeler-DeWitt equation obeys both the Hamiltonian and the spatial diff constraints. So what we need to do is construct a theory that satisfies the Hamiltonian constraint. Actually, the diff constraint is easy. It actually is satisfied let me be concrete here. Let's suppose we're doing 2+1 pure gravity. Okay, so the diff constraint is like, it's probably a factor of 2 here or something, but the diff constraint looks like the divergence of pi AB, which according to this dictionary is the stress tensor. So actually, this is just the expression of covariance. So actually, any field theory will solve this constraint as long as it's covariant, as a covariant Lagrangian.
Now the gravity.
Yeah. So I would call that a non-covariant theory. Yeah, so H looks like pi AB minus pi squared minus r minus 2 lambda equals 0. Okay, and I'm pretty sure I got the signs there, right? And so this is not a usual condition for a field theory to obey. Now notice it cares about the trace. So it's not a conformally invariant equation. So this is definitely not going to be a CFT, but you can show it's a deformed CFT, and this is how. So what you do is you imagine just adding a 2D cosmological constant to this theory. This is just a sort of counter term. So it's really purely conventional. So I can shift pi goes to pi plus some constant here. And when I do that, I can pick this pi naught to complete the square and eliminate this lambda term. And what I'm left with is so you have the same stuff, and then you'll have a term that's linear in pi with some coefficient that I'm not going to bother to work out. And then this thing is going to be equal to r. So in a CFT, we have that the stress tensor T is given by like the central charge, it was 12 or 6 or something, the times r. And so what you see is that this equation looks like the conformal anomaly equation in the limit that you take the square root g, the volume form, and you take it to infinity. This is some analysis that was done to the Wheeler-DeWitt equation by Laurent, and he pointed out the relation to ADS-CFT. So if you take the Wheeler-DeWitt equation, this looks like some irrelevant term in the limit that you blow up the volume uniformly everywhere. So that's the limit where you recover the holographic CFT. And then if you want to go back to the Wheeler-DeWitt, it looks like what you're doing is you're deforming the theory by adding to the Lagrangian of the theory something that's quadratic in the stress tensor and has this particular form. Now, as you deform the Lagrangian, if you want to make this coupling constant finite, it's important to interpret like in a differential equation sense. So as I deform from lambda equals 0, where lambda is the coupling, irrelevant coupling constant, to lambda is finite, say lambda equals 1, then at every point along this flow, I want to be deforming by a term, this term in the stress tensor of where I am right at that moment. Because as I change the theory, I change the definition of the stress tensor. I want to interpret this deformation in a differential equation sense. Or there's another way of writing it in terms of a path ordered exponential acting on the partition function. That's where you think of this pi as this differential operator. So then, one nice thing about this is that this is the same as in the case of 3D pure gravity. You can generalize this by adding matter fields, by going to higher dimensions. That generally requires large N of holography to be under control. But in this pure gravity case, you don't actually need large N. And this theory is exactly solvable, at least on a cylinder. You can get the exact spectrum. Because it turns out that the energy eigenvalues obey a differential equation that does not mix different energy eigenvalues. So there's a clever argument by Zemeljakov. It's true of any 2D QFT. It doesn't have to be a CFT. But it turns out when you write this exact expression down, which is, by the way, the determinant of the stress tensor. It turns out that if you write this, let's see, am I going to be doing this right? I think this isn't quite the same notation as he used, so it's possible I'm screwing this up, but if I make the terms here depend separately on the positions, then a combination of conservation and translation invariance tells you that this thing is actually independent. You can translate X and Y independently of each other and get the same answer. And that allows you to replace an expression like this in the Lagrangian with something where you integrate both stress tensors separately, and then you can rewrite it in terms of the energy and angular momentum. Anyway, when you do this, you get an explicit formula for the deformed energy. And so if you start with this CFT, well, we said you have an explicit formula, but you have to know, since it's a differential equation, you have to know where you're starting. And so if you start with a CFT that has a spectrum of a cylinder given by curly E and J, where J is conserved under this transformation, then the deformed energy ends up being 1 minus in some units 1 minus 2 curly E plus J squared. And now I'm going to restore some stuff. Lambda here is the coupling, and L is the radius of the cylinder. It's really you only care about the dimensionless combination here. So if you, and that's actually true for all of Cauchy slice holography. So if you can just conventionally decide that lambda is 1 everywhere, and anything you could have done by changing lambda, you can instead do by just changing the scale factor of your metric. So you get this expression like this, involving a square root here. And I should say, I'm evaluating this energy in the frame where it looks like the standard Hamiltonian constraint, not the frame where we've shifted it to take the CFT limit. If I was in the CFT limit, there'd be another term out front, and this would not fit on this blackboard. So, but it's just a 2D cosmological constant, so it just shifts the energy by something that's proportional to L. So that's a boring term. All right, so there's a square root here. So if you took this really seriously, you'd have actually two sets of solutions, only one of which maps to the original CFT. And the crazy thing that happens at a certain point is if curly E is big enough and J is not too big, then the argument of the square root becomes negative, and so the energy becomes imaginary. So if I plot the energy in the complex plane, I would get what I call the cross-shaped spectrum, where you have a ground state, the states get higher and higher energy, and it's a holographic theory, you eventually get black holes, and then at some point you take a right angle turn in the complex plane. If you include both sets of solutions, then you'll have symmetry here. Now, in the bulk, once you have a black hole, this is like BTZ with Dirichlet boundary conditions. And the fact that the energy is imaginary from the goal of getting Cauchy slice holography, it's actually good because you see this I sign here. This I sign is telling me that pi AB has the usual sign for to be real in Lorentzian signature, because it's a quantum mechanics momentum operator. The field theory has an imaginary stress tensor. So it's definitely not going to be a standard unitary theory. And these four branches of the spectrum can then be interpreted in terms of the corresponding BTZ black hole.
Sorry to pause you.
Yeah.
Can you go through that argument again
Which argument?
more slowly? The one where, okay, so if I want pi to be real, then T is imaginary.
Yeah, so pi, this is despite Wheeler-DeWitt being like fancy quantum gravity and stuff, morally, this is just a momentum operator. Okay, so it has an I out front. Okay, that's true in Lorentzian signature. Okay, if I whip rotated quantum gravity, I wouldn't have this I here, but in standard Lorentzian quantum gravity so the Cauchy slice is Euclidean, and then I want a momentum when I change things in the time direction.
I understand. You can, I mean, this is a Hamiltonian formalism. It has nothing to do with the other time is real or that.
Well, maybe I could write another equation that will make that a bit clearer.
I go from any unitary evolution, E to I, H T to E to the minus beta.
Right, so one of the same Hamiltonian constraint can do both things. Let me maybe try to say it in a way that will be more palatable. Okay, so there's a formula in ADM that relates the momentum to the extrinsic curvature. Okay, so for any given saddle of the quantum gravity equations, I can then express things in terms of KAB, the extrinsic curvature, but KAB is defined in terms of a normal direction for the Cauchy slice. So the sign of this thing definitely cares whether in the particular saddle, the normal is pointing in a time-like direction or a space-like direction. Those will differ by the I sign. So if you have a saddle of this theory where if you have a gravitational path integral, there's a saddle that evolves up to a Cauchy slice where the saddle looks Lorentzian in the region that touches the Cauchy slice, then the expectation value of this thing will be well, it's real by convention, but only because you have this I here.
I mean,
So-
this is a usual thing that the phase of the wave function oscillates, so you need it.
Yeah, that's right. So there's actually another nice example that's a little easier to visualize, which is if you're in de Sitter and if you're just in de Sitter mini superspace, then you look at the Holographic wave function, then that looks exponential on one side of the transition and oscillatory on the other side. So this is the region where you're doing your gravitational saddle up to a sphere of smaller radius than the center. And then if you're doing it up to larger radius of the center, you need to have a Lorentzian piece of your saddle. And in the Holographic contour, you sum over this going either the future or the past. So you get something that's real but oscillatory. And so the turnover behavior looks sort of like an Airy function. And actually the semi-classical behavior, the semi-classical approximation actually breaks down there, but the mini superspace wave function is perfectly well defined. Yeah.
This may be besides your topic, but in this case, do you get two branches because if it's oscillatory?
Yeah, so one of them's like the plus I something, and the other thing is a minus I. Yeah.
They're both, okay.
Yeah. So the words I would drape around this is on this side where the saddle is Euclidean, the field theory preserves CPT. And on this side, it spontaneously breaks CPT.
Okay, interesting.
Because your wave function is best viewed as a superposition of an expanding branch and a contracting branch that would considered individually break time reverse.
Wait, the saddle points are imaginary. If I'm just thinking the area function. As Herman just said, the two saddle points, what are they?
Well, it's a cosine, so cosine has two frequencies, positive frequency and negative frequency, or positive
Morally,
and
yes.
negative momentum. So the negative momentum means contracting universe, positive momentum means expanding.
Yeah. So this transition is related to this type of transition. This transition of the spectrum is also a CPT broken versus CPT preserved transition. And here I'd like to say that if you're on the real energy axis, that corresponds to radial cutoff holography, where you have Dirichlet boundary conditions going up to some surface that's at finite distance. So that was the original holographic story of TTbar. But if you're on this imaginary branch, it's better thought of as being here or here, where whether you're in the black hole region or the white hole region depends on whether you pick this branch or this branch or the square root. So the extrinsic curvature these slices of these constant R slices, Schwarzschild R, in the black hole matches on to the properties of energy eigenvalues in this TTbar theory. The TTbar theory notes that the spectrum is discrete and semi-classical gravity does not, but there's a correspondence here. So if you're on this branch, that's the other square root of the real axis, presumably that corresponds to being on the other universe.
So for a given CFT and given value of lambda, then there's part of the spectrum for which the square root is real, part of the spectrum for which it becomes imaginary.
That's right.
So the imaginary states live in the interior, and the real states still live in
the exterior. That's right. So when you go from here to here, something's gotta change in terms of the signature. What I've drawn here is keeping the bulk signature Lorentzian. And I'm changing the signature of my boundary theory. There is an alternative perspective, which is you could decide that your boundary theory is always Euclidean. And then in the case we are outside the horizon, your saddle will look like the Euclidean version of the black hole. And it's only when you're on the imaginary axis that it looks like you're in the Lorentzian black hole.
About this sort of mismatch between this knows about the discreteness, the spectrum,
Yeah.
and classical gravity, not. Do you have some speculation as to what the extra ingredient is?
I mean, the extra ingredient is holography. This thing is manifestly holographic from the beginning. So that this thing is a partition function, which means everything is determined what the states of the theory are in D-1, come from D-1 dimensional boundary conditions. So holography is imposed from the beginning. Now, what is the thing that gives in semi-classical gravity? I think the thing that's going to give is that this thing is going to have like null states that weren't obviously null from the Wheeler-DeWitt perspective if you just started quantizing bulk gravity. So a particularly obvious example of this is if I did pick my Cauchy slice to be compact. So if I evaluate on a sphere or something, then I would get, since the partition function is just some specific number, that's a function of this metric and so on, I would just get one particular Wheeler-DeWitt state. So it has a similar flavor to no boundary proposals, where for a closed universe, the holographic theory forces you to be in one particular state. Now, so that would be an example where everything is null except one state. Needless to say, you don't see that in any obvious way when doing semi-classical Wheeler-DeWitt gravity that has lots and lots and lots of possible states of closed universes. I do think this is going to be relevant for the black hole information puzzle, because if you form a black hole from collapse, this would of course require somewhere here. If I add matter to this picture, so that I can form a black hole from collapse, and then you let it evaporate, I have something that comes in here, and now I have some Cauchy slice that comes out here like this. It gives me, so the star that fell in is going to be affecting the sources on this Cauchy slice. Assume that star is in a pure state, that those sources will be in some superposition of pure states. And this thing is just like some like cigar shaped thing. This is like some nice slice. And so this is a partition function with only one boundary. And so it's just manifestly true that there's going to be a map from the possible sources corresponding to the star to some pure CFT state out at the boundary. So from that perspective, because this is a manifestly holographic theory, it's clear that information is not lost. But why is it not lost? Why can't we just stuff this nice slice with explicit sources, maybe not coming from collapse, that have too much entropy for the black hole and too much entropy to the CFT state? Well, because on the spectrum, I can count the number of states there are at a given spot, and specifically if I'm at the center here, it's A over 4. In this spectrum, I point out the density of states here. interpret a microcanonical sense, when you're at the branch point, the density of states is e to the m or 4g.
The branch point between the square, yeah.
Yeah. So in pure gravity, there's fewer states here and there's more states here.
Yeah, this corresponds to the statement that, that the thing becomes
Yeah.
imaginary at the moment that BTC black hole touches the.
Yeah. And this, roughly speaking, is being on the horizon. A more precise analysis I don't want to get into indicates that it's best thought as being on a marginally trapped surface. But, yeah.
Because if we talk about the density of states, talk about the density of states as computed in the original CFT or from the point of view of.
No, in this equation here. Yeah, so there's a fixed S of curly E.
Right.
Okay, and you could just plug that in algebraically into this. Now, of course, since the energy eigenvalues will get a little bit closer and farther apart, there's some leading corrections to this, but that's quite small, so you can ignore that. That's like the usual things where it doesn't matter whether you calculate, canonical or microcanonical entropy at leading order. Okay, so for the leading order, like semi-classical entropy, you just take S of curly E and then write curly E as function of E, and that gives you S of E.
And this formula will give you the area over 4.
It gives you the area over 4 when you're at energy equals 0 at this branch point. It gives you different answers at other places.
But I'm confused about one thing. So you're saying the imaginary part of the spectrum corresponding to some black hole?
The imaginary part of the spectrum corresponds to like being inside the black hole.
Yeah, but
And at this point, there's more states than this area, which is a good thing, because if we were limited by that, then we can make this area arbitrarily small by going close to the singularity. So whereas we know that the entanglement between these two sides is given by the area of this surface. So it would actually be a contradiction if there were not more states than the area on this imaginary axis.
Okay, so in other words, they here compute the area just from the S of curl E, but that does not really count how many states on the imaginary axis. It's just some coarse grain for those states.
It's a core, right? This is a coarse grain entropy, but it's a microcanonical. It's a microcanonical entropy, so that means it counts the number of states in some small interval. But you can imagine a state in that interval that had less entropy than that. For example, if it's a pure state or something, what you can't have is a state in that interval that has more entropy than that. Whatever.
So when you're looking at the spectrum of the states that are in the interior, you only allow states that have energy that are close to your critical energy.
Well, you'd only allow states that are close to whatever your extrinsic curvature is. The idea of this equation.
But in terms of the spectrum of the CFD, it means that we're always close to this.
Well, you're always close to some specific value of remnant party. Yeah. But you have to invert this equation to go directly. You have to use this equation to see which value of E that is.
I guess as you approach the singularity, the extrinsic curvature blows up and you're.
So there's some sense in which going to infinity in this direction is like a Hagedorn type behavior where the number of states grows exponentially, and there's some limit. The limit where you go to imaginary energy is in some sense the same as the limit where you approach the singularity. The one subtle thing about that is if I hold the mass of the black hole fixed, then I will need to simultaneously adjust L to match the area of the space-time. Actually, there's another subtlety, which is all this is the pure gravity answer, and when I start including matter, things get badly messed up on this imaginary axis where it appears that you could actually make the entropy arbitrarily large, but that's another story.
Let's see, is there some interpretation for the entropy, not at the cross, but the entropy at some other location?
Well, from the field theory point of view, I would call it microcanonical entropy.
Yes.
From a bulk point of view, I would call it entropy bound. So given data that exists on a codimension 2 surface, it limits the amount of entanglement you can have between the two sides in a way that's morally somewhat like tensor network bands. And now to just complete the idea I was making here about the information puzzle, because we have a bound of A over 4 that isn't the horizon. So here S is less than A over 4. That tells you that whatever happens here in terms of sources, by the time I reach this surface, no later than the time I reach this surface, there has to have been a post-selection down to at most A over 4, either the A over 4 states. And that post-selection would be like the presence of null states that the semi-classical approximation doesn't know about. And to me, this is the thing. This is a thing that goes wrong, similar to the it's more like the Python's lunch story that makes it so that it's this post-selection is the discrepancy that semi-classical physics doesn't know about that makes it possible for the entropy to escape.
That part of the story I like. I think I missed how this post-selection is supposed to take, in the presence of null states, is supposed to take a theory that has a seemingly continuous spectrum and then give you one that has a discrete spectrum. So once we consider null states, how does it?
Oh, well. I mean, I don't know, it's obvious that just having null states would give you a discrete spectrum.
Yeah.
It's just that we know this theory does have a discrete spectrum if we obtain it from a holographic CFT, so.
Yeah, it's not obvious, right? I guess the question is, do you have to have some other part of the story to explain that? Or
What I'm not saying
already-
is that I can take semi-classical gravity and
Yeah.
fix it up with bells and whistles and see that it's the same as this. Rather, I'd like to take the holographic point of view as the fundamental point of view, and then try to say that semi-classical physics is good in some regime.
Yeah, I guess this energy is somehow momentum, right? It's just the
Yeah,
evolution in the
well, it's momentum.
inside the black hole.
Sorry, you mean, if you were living on this slice, you would think of it as a momentum?
And in the
It's more like another charge of momentum.
yeah, it's the charge associated to evolution.
But it's a boundary charge because it lives on codimension
Yeah.
2 surface. So it's something like if there was momentum, it would need this boundary charge on one or the other side of it, something like, I think that's right.
Guess a related question.
Yeah.
So the time flow in the CFT isn't the thing that brings you along the spatial slice interior. Right. Is that right? Because yeah, time flow.
That's right,
from
that's
the
right.
interior goes up, and let's say in the interior it goes, say, from left to right.
Yeah,
What you call E is indeed the eigen value of that particular time.
well, I mean, this E is with respect to the proper time of the slice.
Yeah, is it that proper time or is it that proper time? Is it that proper distance?
And well, because this is imaginary, it would have an I side relative to the usual notion
Yeah.
of energy. One way to put it. So this branch corresponds to the wave function behaving in an oscillatory manner. This branch also corresponds to your eigenvalues behaving in an oscillatory manner, and you're just surprised because it was a Euclidean field theory that's oscillating instead of a Lorentzian theory that's oscillating. And the fact that it's the Euclidean theory that's oscillating is what corresponds to the stress tensor being imaginary. But there's a sense in which the Schwarz, with respect to Schwarzschild T, you have oscillations of eigenvalues regardless of whether you're inside or outside the horizon, which is probably important for consistency. Yeah,
All right, I have a very naive question.
good. The naiver, the better.
Do the null states that you were describing, I was a little bit confused by the discussion earlier. Do the null states that you were describing have a nice semi-classical description?
Well, I mean, the point is that there exist states that have a nice semi-classical description that whose dynamical inner product would be 0 or something when calculated by this holographic means.
But I guess.
They get projected at.
Like in the example that you were talking about before, you're talking about working on the Cauchy slice, and your argument is basically that if I add in enough states with enough entanglement, it will have area, like it will have entanglement that is greater than the area of the black hole. Right? Or it seems like the example you gave previously of this of a null state, which is a state that has a large amount of entanglement seemingly that needs to be projected down. It seems like.
Well, I said entropy, not entanglement.
Okay, entropy.
If you actually make it entanglement, if I was trying to, if I have a bunch of like quantum fields here that are entangled with quantum fields here, and I connect them up, and I think of these as extra tensor network lines, then it appears at first sight that I'm actually increasing this maximum entropy bound because I have these extra tensor network legs. But there's an important caveat in that, which is that's only true if I regard this entanglement as a resource rather than something I'm itself trying to reconstruct. So I think the generalized second law is basically going to tell you that as long as you regard the Hawking pairs and their partners as a resource, and you're using that resource to calculate what was in the star, then you're always going to be able to succeed without any post-selection needed. But if you want to go further, if you want to say, I want to reconstruct both the star and the partner modes so that I can check explicitly that they're entangled with the Hawking radiation, that's too much. Because if I want to interpret these things as a part of my signal, then it goes to the other side of the entropy bound and it makes things worse instead of better. If I think of it as like logical qubits that I'm trying to reconstruct.
A question about inner product. So from the point of view of the boundary CFT, you could say, hey, the boundary or the CFT that we started with,
Yeah.
and there's an inner product on that outer space that simply makes, say, energy United States orthogonal. Are you imagining that what happens if I want to do quantum mechanics in the interior? Can I use the CFT inner product, or should I write down some kind of Wheeler-DeWitt inner product?
Right. So the first thing is if my Hamiltonian is self-adjoint with respect to a positive inner product, then I can never get this type of behavior. So, but I can get it if I suppose that my T-squared theory has an indefinite inner product. So if I have some positive norm states and some negative norm states, if you think that the states coming in from this branch that correspond to the original CFT states have positive norm, and these states correspond to negative norm, it seems conceptually possible. It's possible to write down Hamiltonians that are smooth, where two eigenvalues come in and then pop off on the imaginary axis. This was sort of what my seminar a couple of weeks ago was about. From that perspective, you would say, okay, these states have positive norms, so they're okay. But something funny would be happening if I tried to do quantum gravity in like this wedge region here, then I would find that my holographic dual states that I kind of mentioned live on this surface aren't really a proper Hilbert space. So on the other hand, if I sort of stay outside the black hole, then I can restrict it to, and I'm just on this branch, then it looks like I do have a positive norm Hilbert space restricted to that situation. So it feels like what the math is saying maybe is that it only makes sense to talk about quantum gravity in a finite size region and have a probability interpretation if the boundary convention to surface has like a space-like extrinsic curvature instead of a time-like extrinsic curvature. Now, since a lot of people thought it wouldn't make sense to talk about quantum gravity in a region with a boundary at all, I would say this is still an improvement relative to the baseline. And it might conceivably be related to the entanglement wedge idea, that there's some natural sense in which the CFT is dual to the wedge region that goes up to the surface where the extrinsic curvature vanishes. That's sort of like saying you could go up to this point, but no further. Or if you do go further, you encounter these negative norm states and you get confused.
When you talk about these states, these are the states in the field theory, right?
These are the states of the field theory.
Because there's another notion of states in the Wheeler-DeWitt that will also.
That's right.
Discuss whether it has they have positive or negative norm.
Yes, but of course you might think that if the holographic dictionary that agrees that the norms, the bulk norm has to agree with the boundary norm. It would have to be a.
I don't see why those two notions of states are the same. So here the state is the partition function. Sorry, from the Wheeler-DeWitt point of view, the state becomes some particular partition function or some particular field theory.
Well, you could construct a story that's like this. You could say, suppose I have a finite size interval region, a partial Cauchy slice sigma 1, and I want to define an inner product with some other data on some other slice sigma 2. Then what I could do is, well, first of all, I want to do a CPT transformation to actually like complex conjugate this guy to get a proper accessible lineal form. But ignoring that issue, what I want to do is let's assume they have the same boundary. Otherwise, it probably doesn't make sense if I hit a product on them. Then what I could do is I can simply glue them together. From a field theory point of view, this is now a closed partition function. And so the Z of this is just some number. And it's natural to try to then say the bulk dual of this is it's like calculating the amplitude in the gravitational path integral to evolve from sigma 1 to sigma 2.
Well, I mean, when people discuss the Wheeler-DeWitt wave function, there is an inner product on this wave function.
Well, yeah, but the one they usually discuss is not one I like very much.
Yeah, let me finish the.
Yeah.
So because this Wheeler-DeWitt equation is second order, then this inner product is a bit like you can define something like a Klein-Gordon inner product, which will not be positive. Then people discuss some other inner products. So there is a whole discussion of what inner products are. The Klein-Gordon. Now that inner product is not obviously related to me. Well, this does not seem obviously related to the inner product in the field theory, in the d-dimensional field theory for states in the d-dimensional field theory.
I agree. And so in our Cauchy slice holography paper, we only discuss this Klein-Gordon norm in a footnote to explain why we don't care about it. The thing we think is the right dictionary is that if you want to define a dynamical inner product by using the gravitational path integral between sigma 1 and sigma 2, then that's the thing we think should match to the inner product.
Is this inner product positive? That mean.
Not obviously. Actually, that's a very subtle question. Whether it's positive or not. But it certainly doesn't treat plus signs and minus signs on equal footing the way the Klein-Gordon does. So it's sort of an open question. There's a hand-wavy semi-classical argument based on evolving to maximum volume slices that says it should be positive, but it's not a very vigorous argument.
But does it correspond to a bulk computation? So you described it in using what would be the holographic field theory discussion, but is there a bulk definition of this inner product that?
Semi-classically,
Yeah,
I mean,
relative.
formally, you know, you would write down a path integral over all the metrics that begin here and here and evaluate the action.
Well, I was hoping you would give me, we would have two Wheeler-DeWitt wave functions and you would tell me how to do the inner product.
But that's the boundary conditions of this thing. So this is a D+1 metric. And we need to specify boundary conditions. So what we say is that on sigma 1, this G equals G1, and on sigma 2, this G equals G2, where G1 and G2 are the metrics on these Cauchy slices. That there's still some tricky questions about what contour you're using. But this path integral naturally takes the data on these Cauchy slices as boundary conditions. Yeah.
I got a question, going way back to your Z of sigma for the T squared deformed theory. Suppose that the sigma partition function, suppose it's a product of circle, you know, it's one example.
Okay.
Let's suppose it's a product of few minus 3. Then I can use your formula to say that the partition function has to be trace of e to the minus radius of one of the circles. That's the Hamiltonian.
So which formula?
The formula for the energy. Yeah,
So this precise formula is valid for the 2D case. So can we do it?
Let's take the 2D case. So what do people say about the partition function on the torus for the T squared deformed theory?
Right. So in our approach, where we want to keep these imaginary energy eigenvalues, it doesn't seem that would be defining like a canonical ensemble. And while the microcanonical
Partition function doesn't exist. I mean,
it does not. I think it does not because there's a lot of states here, and there's an oscillatory contribution times like an exponentially growing.
E to the minus trace of e to the minus beta h.
I agree. So what seems to be true though is if you take your beta of this torus and you smear it a little bit, then I believe that controls this divergence.
Spirit.
Spirit.
Or what do you mean spirit?
Spirit, like.
I mean, think of it as a distribution.
Think of it as a distribution over like some Gaussian of nearby beta values. That will suppress this contribution. And so on the one hand, you have the smear beta. On the other hand, once you do that, it seems like the partition function makes sense for negative beta values as well as positive beta values. So that's a way in which it's better. We are still thinking about checking modular invariance of this thing. Because of the smearing, you'll have to sort of generalize your appropriate notion of modular invariance. But I believe there's a non-trivial, interesting check to be done here. What people have shown in the literature, I've been told, is that the spectrum is modular invariant considered perturbatively in lambda.
like order by order lambda, but because something so dramatic happens to the spectrum at finite lambda, I think we really want to know the finite lambda.
You look at the correlation functions of some operators on the torus. You perturb them. That's not surprising.
Yeah.
So I have a comment also, and I don't know if it's relevant, but I'll make it. Which is that, in supersymmetric gauge theories in 4 dimensions, there's a whole, industry that looks at partition functions of surface defects and interprets them as wave functions.
Okay.
And the nice thing is that that's all rigorous, so they're wave functions for what are called the quantum zone.
Good. Yeah, I can believe that. The
Relevant to your story.
right. It's certainly.
Function of a defect is actually can be thought of naturally as a wave function.
It's certainly relevant to my talk I gave last time, where you could take these things like bilinear forms and so on that I was discussing. You could think of them as claiming the existence of certain sorts of defect operators, d minus 1 dimensional defect operators in the theory. I didn't say it in that language, but it might be illuminating to translate everything into that language.
Could you mention what you see as the major open questions remaining for this program?
Good question. I mean, to me, the biggest open question is that once you aren't doing pure gravity anymore, it's not the solvability of this type of thing is requires large N, and it's an irrelevant deformation. So I would like to know whether it's possible to UV complete this kind of model and make sure that the field theory is actually constructible. I believe doing so would provide a non-perturbative definition of holographic bulk gravity. So that seems important. There's several other important questions we touched on, like if there's negative norm states, you've got to do something. You gotta ask under what conditions can we get a positive norm and apply the Born rule properly. With respect to the information puzzle, it would be good to make this story more concrete. Identify what kinds of null states there are. And again, at the level of interpretation, which might be a very hard interpretation quantum mechanics problem, but if this is the right story, you could ask yourself the question that all the people have been angsting about the journalists answering wrong, which is, has the information problem been solved? And to me, if we showed that this was the story involving post-selection, there's one very important task that would remain to be done, which is coming up with a coherent story of what the infalling observer experiences, given that there's this post-selection step. There's lots of technical problems too, of course.
Have you tried to do this in 1+1 dimension, when the bulk is 1+1 dimensional?
I have. So master's student who Rick Chang at Cambridge, well, he was last year, and I worked on a model of a non-Hermitian quantum mechanics that turns out to exactly solve the constraint equations of dilaton gravity.
And we start with something known, like maybe the SYK model. Well, yeah.
Well, that we have not done. Other people have done things that have tried to do things like TTbar deform SYK. The thing Rick and I did just gives you pure gravity, and to talk about things like the information puzzle, you really want at least one matter field. So. But yeah, that would be an obvious direction to go. Is to try to, I know people have tried to have done papers where they've like tried to TTbar deform SYK, but this approach suggests that you should then ask what happens when if you go into the black hole region and so on.
Yeah, I think my understanding was when people discussed TTbar deformations of this 2D gravity, there were different possible answers, and it was a murky. I don't know if it's understood. Maybe it's understood. I just don't. That's my impression. You know that there is a well-defined answer in that case for TTbar deformation of boundary.
Right. So that's why the perspective I was sort of trying to take in the previous talk was to sort of go the other direction, just ask like, what's the symmetry class of the theory? And then you could sort of ask, what maybe generic Hamiltonians in that symmetry class do, or to try to write down some matrix model that's in that symmetry class. And then you try to see if something like dilaton gravity and matter emerges from that.
Okay, thanks, Aaron. We'll save the rest for lunch.
Okay.
I have another question.
Yes.
So this was orthogonal, I think, for the gravity discussion. I can think of TTbar as like a type of regularization procedure for my theory. Do you think this like picture of null states is like more generic? Is like a generic way I should think of I do like any kind of renormalization? Because when I do any kind of renormalization, I usually have to impose some cutoff. And I do some kind of statement that I'm like ignoring the state.
The people who want to throw out these imaginary energy eigenvalues, maybe what they're doing could be cut off. But it's not obvious that this is really a unique cutoff theory if you keep the imaginary energy eigenvalues.
I had a different comment. So regarding the story of post-selection and what then the interior observer observes, this is I agree, a very good question. We have a whole discussion of this in our non-isometric codes paper. I would be interested to hear your thoughts on that discussion. I don't know if you read it, but
I believe it.
yeah. Well, in the talk, we never find focus on that. That's why I bring it up, because there's a whole section literally on like what the interior observer would observe. Because I think a very subtle aspect of this story.
I just have a theme for a conference. Instead of picking like a particular like physics theme, you say it's that section of your paper that you never have.
Right.
Talks. Just talk about that one.
That was exactly.
Maybe you just invite all the cool people who are going to giving talks, or
yeah, we get. I pick some paper that everyone has. Yeah, like exactly the West Coast model paper, like Douglas Stanford would tell us about section 6, and then
or everybody picks the paper, but they have to hear about the part that nobody's heard about.
Yeah, right.
So you end up learning about some obscure fact about this paper that's widely cited, but nobody actually fully read.
Yeah, exactly. So one thing that I think historically was underappreciated about, say, a setup like this is that how this interior, like with all the yellow modes and the white modes, is encoded. Like let's imagine it like a tensor network where you're just gonna like say push from here to here.
Yeah.
So you're gonna regard it as a state on like these degrees of freedom and maybe some radiation modes there. That's just that's some linear map that is fixed regardless of what the state is. And so you're encoding all of these degrees of freedom into this smaller set. And to me, there was a big mystery 3 years ago as to how that could possibly be consistent. Because how could you possibly have some good encoding that acts approximately isometrically, into a smaller number of degrees of freedom. And so that's mostly what our paper is about. And we show that this actually is possible. But it has
Pretty
to,
sure I saw Dan Harlow give a talk about something related to this.
yeah, this is my paper with Daniel Harlow.
Okay, well then I do believe I have seen a talk about that aspect.
Yeah, that aspect, because that was the main thing that we wanted to emphasize, because I think it was the most surprising thing. Then you can ask, what are the implications? Once you get this encoding to work and you realize its properties, then you can turn around and ask this question that you were bringing up.
Yeah, but now I'm saying there's another semi-resolution, which is if you only care about the white modes, apparently you don't even have to do that.
See, okay, yeah, that was the way I was thinking about it pre-2022. I think that that's sort of a red herring. I think that we shouldn't really think about this sort of state independent reconstruction where you try and freeze some modes and unfreeze the others. You can do that. I think that's.
I mean, the fact that it works because of the generalized second law makes me think maybe there's something profound about it, but.
I mean, the generalized second law, I think, it fits equally well.
But if you want to just say, I also want to reconstruct something about the yellow modes, then you have to tell your story.
You certainly need to if you want to reconstruct everything. My point of view is that we don't have a choice whenever we're talking about how this is encoded. It just is encoded, all of it, on this side of the red line.
Yeah.
We don't have a choice. You can sort of squint and reinterpret that encoding as sort of only encoding the white modes, and then you could talk about state independent reconstruction. But that is, I would say, derivative of this more general structure that we outline in the paper.
Okay.
Sorry, I just bring this up because I think that we care about the same questions. I wanted to mention the language I use now.
So then, suppose you're an infalling observer.
Good.
And you want to make predictions, but there's going to be this post-election in the future.
Good.
There's
post-selection in the holographic, in the map.
Yeah. Suppose you believe that that's actually like part of the physics.
Yeah.
So I want to not take it into account.
Right.
Then I've wondered, I think this is a very hard interpretational problem, but I'm wondering if it's actually equivalent to more standard interpretation of quantum mechanics problem that we've just been sweeping under the rug.
Okay.
Which is making predictions about the past, or not assertions about the past.
Okay.
So there's this thing called two-state formulations of quantum mechanics.
Right.
We have both an initial state and a final state,
Right.
and then you want to talk about what happened in between.
Right.
And
Yeah, and then you get acausality and so on.
I mean, there's various unpleasant things, but this is the sort of thing that Copenhagen instructions sort of try to make you ignore this problem as much as you can.
Yeah.
But if you want to say something like there were dinosaurs,
Yeah.
that's going to be a combination. That the facts you use to deduce that there are dinosaurs are some combination of measurements you make in the present day, and that's not enough. You also need a stipulation about the universe starting in a special state.
Good. Like some low entropy states.
Some low entropy state. In fact, which I take as shorthand for some specific low entropy state that the cosmologists tell you what is.
Right.
Okay.
Sure.
So the thing to note is that if the projection operator onto that low energy state and the projection operator onto there being dinosaur bones in the ground, they don't actually commute with each other.
Okay.
So if you actually think you know both of these things, you actually know more about the universe than the Heisenberg uncertainty principle would naively allow. Okay. And so we're definitely doing a very non-standard problem. But it seems like you have to be able to solve that problem if you want to be able to say that there really were dinosaurs.
Yeah.
And maybe that problem is isomorphic to if you assume that this sort of bottleneck story, Python's lunch, whatever you want to call it, is accurate. I feel like maybe the remaining piece of the black hole information puzzle is isomorphic to that problem.
Wait, sorry.
Let me give you a different perspective. Sorry.
Well, let me just say where the state on the pink thing
Yeah.
is on the bottleneck
Yeah.
is the dinosaur bones at the present day. The star is the initial condition, and the experience of the infalling observer is the dinosaurs.
Can I ask one quick question about the dinosaur example? Sorry, because I know your
Yeah.
questions are sorry. Wait, why can't I just take my Hamiltonian and then just evolve back in time? Why do I need to know the start of the universe? Like,
Because if you don't stipulate that the universe began in a low entropy state, that evolution back in time will be increasing in entropy instead of decreasing. If you start with a good cosmology, you evolve it forwards in time, and then you project the state at that
oh, okay.
time to something being true. Now the state is mostly orthogonal to the cosmological.
Yeah,
state.
okay, sorry.
And when you evolve that back in time, you typically will find that entropy is now growing.
Yeah, okay.
So the dinosaur bones that are in the ground will just keep decaying as you go back in time.
Yes. No, that makes sense. I was thinking too classically. Sorry, Chris.
No, okay, I want to propose a different point of view, which is that if you take the perspective that this stuff is being encoded, this stuff is all being encoded here, and for that to even work consistently, there are certain rules you have to obey. Like it's the sort of the simple states, perhaps, who have their inner products approximately preserved, but not all states. That's impossible because it's a non-isometric map.
Yeah.
If you take that seriously, what could be the story is that you shouldn't even really worry about the physics of this post-selection. That was something that was certainly worrying in like the final state proposal, which feels mathematically similar. But the difference is that as long as you're doing only, say, simple operations, keeping yourself in.
Right, so I agree that there's these quantum information theorems that seem to say that as long as things are random enough, as long as you get under the post-selection barrier, you expect the inner products to only be affected by like exponentially tiny events.
Yeah, which let's take that as we need that to be the case. Otherwise, effective theory physics would just be completely violated. So if we want effective theory physics, like semi-classical gravity, to be even approximately correct around here, then we need the inner products of at least these states to be approximately well preserved by this non-isometric map. If that's the case, I think there's a good argument for just not really worrying about this as some final state post-selection. It's you don't have to think about it like.
Well, that's for the simple ones. So if you then turn around and say, if I measure something non-simple, then you do have to worry about it.
Yeah, so that's the problem. Is if you do something exponentially complicated, you should just not trust the effective description at all. There's just no reason to trust the effective description in that case. The effective description is some emergent thing that works as long as you're not doing anything.
Which could just mean wanting to know everything.
What?
Which could just mean wanting to know everything.
Yeah, I think my point of view would be that, right, this effective description is, involves many more degrees of freedom than the fundamental description. The one that you get from the dual.
You have to not ask too many questions.
Right, it has junk information in it. So if you're trying to probe that junk information, it's just actually not there. That's part of the point.
Do you think this solves the trans-Planckian problem?
Meaning, oh yeah, like when modes enter.
Well, the problem is that on the one hand, we'd like to think that like there's some UV cutoff at the Planck scale.
Yeah.
That cuts off the entanglements.
On the other hand, there's things like
At the
red-
Planck scale, so you get S equals A over 4G. On the other hand, Lorentzian variant suggests that's not actually possible.
Yeah.
Because highly boosted observer would see more and more blue shifted modes closer and closer to the surface.
Yeah.
So is the answer that those modes are all there in the effective description, but somehow you're just limited to how many you can measure? So that in some sense, the if you boost if you have like a boosted variant description, but if you boost too highly, you get things that are like redundant with the stuff you have so far or something.
If you try and measure too,
Yeah. Something like, I think something like this.
if you measure too many, you just collapse into a black hole. And then you're not measuring anything.
Well, but what about your
What?
experience before you die in the singularity?
Oh, when you're falling in.
Yeah, I think,
If you didn't have this point of view, if you thought that everything conglomerated and there wasn't such a thing as measuring too many things,
Yeah.
then you could just talk about what modes any one individual could measure.
yeah,
And then just say, these are all the modes there are, now there's too much entropy. But you're saying you can't do that.
right. And then if you try, you start to see a breakdown of quantum mechanics. And this is the subject of our section where we're talking about what the interior observer observes. So in this, if he only does simple things, then he won't see any deviations from quantum mechanics. And then the question becomes subtle exactly when he tries to say, look at too many things, do too complicated of experiments. And then we propose a formalism from this perspective to tell you what he sees. And it'll be something that deviates from quantum mechanics. Basically because, yeah, there's fewer degrees of freedom than he thinks there are.
I'm wondering if the generalized second law is something like a requirement that you don't have like many states involving diffuse states under time evolution, like that you can't have like. Suppose I specify data t equals 0, some semi-classical data, and I evolve it to the future. Suppose you claim you know how to evolve it to the future. But if I found that there was a bottleneck that had smaller entropy than for my initial condition, you would say, no, that can't possibly be the evolution because it post-selects too much. I would need I would, if I always evolve to some particular geometry in the future, that geometry needs to have enough information capacity to support whatever information I had before.
Yeah, whatever true fundamental information.
Now, once you have Hawking radiation,
Yeah.
and you think about quantum superpositions of Hawking radiation, there's a little bit of a more wiggle room there because you're thinking about quantum superpositions of different space times. So it could be that, a particular branch of the superposition is just unlikely and you're okay with that. But in the sort of classical regime, that can't happen, right?
Yeah.
Because you have a predictable evolution classical.
Uh-huh.
So maybe the generalized second law is like the statement that even when you take into account quantum effects, your like expected size of your bottleneck has to grow on information theory grows.
Interesting. And this second.
And this is if you don't project onto specific states of the Hawking radiation.
So, yeah. In this context, the second law is like coarse graining the area degrees of freedom, but computing the fine grained entropy of the effective degrees of freedom.
Yeah. Well, the entanglement entropy. So it's sort of a.
The entanglement entropy of the effective.
So it's the entanglement of these yellow modes across the surface.
So what happens though if from this point of view, if I like I form a black hole from like maybe the star, it's like entangled with some reference or something, but it's not that much, say. It collapses, forms this black hole, I watch it evaporate, and so there's like these partner modes. So far, it's all the normal story. Then I go and do a measurement of these outside guys in some simple basis. So I get like 0, 1, 0, 0, whatever. So I break the entanglements. at least in my branch of the wave function. And I could have done this sufficiently late such that the initial entropy of the star was greater than the remaining horizon area. So now it looks like there's like an actual bottleneck that I've created. Yeah, I guess. What is the GSL? Like the GSL, I guess in this context works from the global wave function point of view, and not from my. I'm not allowed to do like projective measurements like this and use the GSL, I guess.
Well, if you did do projective measurements, you might think that sometimes the entropy will like fluctuate downwards or something.
Yeah.
But also you might think, you're saying if you measured everything and you project it onto it, then you get like a pure state or something.
Yeah. And like
You definitely shouldn't do that.
Yeah.
Or if you do that, then I guess you have to be okay with the entropy going down.
Right. So it seems like the GSL should be fine here if I kept the point of view that I'm just some quantum system entangling myself with the radiation.
Yeah, but maybe maybe we need a perspective where it's like, okay, if the post-election bites you if you do that, but not okay if you don't do that.
Yeah. From the encoding point of view, actually, you can work out that what happens is so in this case, before you do the measurements, there's some operation you can do on the radiation that tells you like what the state of the star was, or so on. You could reconstruct the diary that was the star. If you do the measurement, you can imagine this as sort of quantum teleporting that information back to the black hole, as long as this isn't too small. If this isn't like exponentially small in the entropy here, then doing that measurement doesn't destroy any of the relevant information. It just sort of puts it back here. Like now you could go to the black hole if you could act on those degrees of freedom and reconstruct the state of the star. The reconstruction map would depend on the measurement outcome, of course. That's the